Most of the algorithms that we encounter have to do with mathematical computations, string processing, but there's a whole range of algorithms that revolve around different domains that have different kinds of structured data. The one we're going to talk about for this module has to do with some algorithms over two-dimensional points in the Cartesian plane. For example, if you have a set of points, sometimes you might ask which of those points is closest to a target point or a query point. And the obvious solution would be to just search all of your points and find the one that's closest. And using our algorithmic formalism, that would be linear behavior, or big O of n. Naturally, I want to try to find if there's any way we can make this better. If you recall, when we had a phone book and we wanted to find a number in the phone book, since it was sorted by last name, it was very quick to find one. In fact, it turned out to be a logarithmic operation. Is there any way that we can structure the points so that we could in fact have logarithmic behavior? Should we be able to do so, this would be a really useful utility. For example, there's a lot of situations when you want to find the ideal arrangement of placements of fixed resources so that you can find which one is closest to a particular incident. This is used, for example, for fire station location, an ambulance location. Or if you have a massive amounts of data along multiple dimensions, you might want to do spectral or clustral analysis to find out groups of points that are close to each other. So if we can figure out this problem in 2 dimensions, it will also scale to multiple dimensions. Let's get started. If we are going to find a way of getting logarithmic behavior, we have to find a way to break the problem up into smaller subproblems, each of which is about half the size. Now, when you're searching in a sorted array, you can use binary array search to cut the problem size in half each time by looking at the midpoint and determining whether to look in the left array or the right array. But when I've got points in a 2-dimensional plane, it doesn't seem to be any immediate way that I can subdivide them up, because I've got an x and a y coordinate. Well, which one do I divide on? And if I could figure that out, then I would truly be able to get my logarithmic behavior. We will be inspired by the binary search tree, which found a way to separate nodes by having a left child and a right child. And they encoded a binary search tree property where you knew that all the values in the left-hand child were less than or equal to the node, and all the values on the right-hand side were greater than or equal to the node. Taking that as an idea, this concept called a KD tree, which stands for k-dimensional tree, which was invented in 1975, is that you want to partition the space using the 2 dimensions. And if we can do this, we can actually, as I mentioned before, scale it up to multiple dimensions. Some applications, for example, come to mind. The eHarmony website tries to find matches among suitable partners along 27 dimensions. And you would want to find 2 points that are close to each other in a 27-dimensional universe. But luckily for today, we're just going to focus on 2 dimensions. Here's how you might go about doing it. If I can look at my space that you see there, I'm picking out one particular point, and I'm going to divide the space into 2 parts, a part on the left and a part on the right. If I choose that first point wisely, well, I've been able to divide my space into 2 sets, each of which is about half the size of the original. So far, so good. The trouble is, if I continue this process using vertical lines, I probably will end up with very thin slices that don't break the problem up into half. What I could do, however, is switch orientation, and now consider breaking up those 2 regions in half horizontally. So I have a top half and a bottom half. And if you look at what you've just done, I have 2 different division points, and I have 4 quadrants created from that. The first one arbitrarily selected as being vertical, and then the next 2 are horizontal. If I continue this flipping, now I have 8 regions. And if each one of those is more or less the same size, then I've broken up my problem into regions of n over 8. And as you can see, this can go on until you have covered the entire space. So this observation is useful, but can I do anything with it? Well, the good news is you can. And what you can set up is a k-dimensional tree, which still has the binary tree structure that we're familiar with. Every node has 2 children. Every node has a value. But we're going to go one step further and start to associate interesting regions with each of these points, as well as an orientation to make it all work. Let's show that in more detail. If every partition that I'm interested in is a rectangular region, and I associate every node with our partition, then I found a way to connect these 2 structures together. You start with an infinite space, infinite on the left, x, y, and infinite from the top to the bottom. That root node represents that large rectangular region, and the partitioning line divides it up into 2 semi-infinite spaces, all the points to the left and all the points to the right. When you look at the children nodes that are rooted off of that node, you'll see that each one represents a region half the size of its parent. And by flipping the orientation, I'm making it possible to truly subdivide the problem into problems that are half as big, then a quarter, and then an eighth as big. Now, this particular red rectangle here is associated with the black point that's right inside of it. This is also in the tree that you see at the top, the leaf node on the left-hand side. And you can imagine traversing a binary tree like we've done before. You start at root node and you choose to go left or right. And then you continue that process until you get down to this red rectangular region. Now, we can't use the words left and right anymore because those only assume a one-dimension x-axis. So I have to find some way to figure out how do I do left, right, top, and bottom. Well, the way that it's done with a KD tree is to come up with a unique concept, which is above and below. And we choose to represent those concepts in one way if you're a y dimension partition, and you represent it another way if you're an x dimension partition. So I start with my root node, which breaks the space up into 2 halves, a left half and a right half. We're going to arbitrarily break up the points such that when I think of the vertical partitioning, there are points to the left and there are points to the right. The points that are above the vertical partition are the ones to the right because their x values are higher. The points that are to the left of the vertical partition are below because their x coordinate value is smaller. When it's a horizontal partition, as you see here with this red, it's actually easy to understand because the points that are above are the ones whose y values are higher, and the points that are below are the ones whose y values are smaller. So we'll keep that in mind. When you see the word above and below, think in terms of the value of that coordinate, whether it's a smaller number or a larger number. Now we need to store additional points with every node in this KD tree. The root, as you see here, the tree, KD tree, just has a single root node, and that's what you would expect in a binary tree structure. Now let's look at each of the nodes. They each have to remember the point that they're trying to store. That makes sense because those are the valuable points I'm trying to remember. They also have to remember what's the orientation of that point in the KD tree. We start with the root and we arbitrarily choose that to be vertical. And at that point, it's associated this constant vertical. The children nodes of a vertical node are always horizontal nodes that split up the space into a top and a bottom. And once again, you flip one more time. So the children nodes of a horizontal are always vertical. And this alternates back and forth. And by doing so, you really are able to partition the space up into these rectangular regions that get smaller and smaller and eventually cover the entire space. To keep all these bookkeeping together then, I want to associate not just the point and the orientation with each node, I also need to keep track of the region. The region will become clearer when we see the code, but here's the intuition. These KD trees can grow just like a binary tree can grow. And when you add a node to a binary tree, you just find where it's located and you insert it. To add a node to a KD tree takes a little more work. You still traverse following the above and the below links to find where it would go. And once you've found where it goes, then you have to create the region that's associated with that node. And the way that you do that is by going to your parent node and finding its region and splitting it up into 2. If you're a horizontal node, as you see here, this red indicated one, then you're going to break it up into a top half and a bottom half. If you're a vertical node, then you're going to break it up into a left half and a right half. And I need to record all of those with each node. And so I introduce this data structure called region, which keeps track of a min and a max x value and a min and a max y value. And so by that means I'm able to represent for each node what the region is that it's representing, the partitioning point upon which that region is separated into two parts, and the orientation that tells me whether it's a horizontal or a vertical partitioning. Let's now implement the KD tree structure in Python. As you know, it is based on a binary tree structure. We'll start with the topmost definition of what a KD tree is, and it will start with this notion of having a root. We'll create an empty KD tree. Initially, it's empty. And what I want to do is be possible to add points to the KD tree, not just values. I know that they're a point. So let's add a point to this KD tree. If the KD tree is empty, we're going to arbitrarily decide to use a vertical partitioning for that point. Otherwise, we have to let the KD tree determine where the point should go. So if there is in fact a root, then we'll have to add that point. Otherwise, we'll just make the root ourselves. And we'll start with the idea that it's vertical. I need to define some constants now to make this work. We are going to arbitrarily choose horizontal and vertical to be two values, but we're going to be a little bit smart about it. We're going to choose two values that I can easily determine how to flip from horizontal to vertical. So I'm going to make them 0 and 1, because if I have a particular orientation, whether it's horizontal or vertical, and I subtract it from 1, I get the other orientation. This is a very easy way to quickly flip from child to parent and child again. I need to define a KD node. And so it's going to store a bunch of information that we've talked about. This creates an empty KD node. This empty KD node is going to have a structure, which we've talked about. Now, when I create a KD node, I have a point in mind, and I have an orientation. So let's get that to work first. I'm going to keep track of the point, and I'll keep track of the orientation. And as we've mentioned, a KD node has an above and a below that could be potentially children. And I'll start off by saying that they're empty, that there is no rooted tree below it or above it. And we also mentioned that every node is going to store its region. So I need to introduce that concept too. Now, regardless of what programming language you have, you probably have access to a rectangle concept or a class. But I really advise against using the built-in rectangle class for this purpose. Most of the rectangle classes have an XY coordinate, and then they have a width and a height. And that just makes it more complicated in the long run. You should introduce a region that keeps track of the minimum and the maximum X and the Y values. It's easy to do, and we'll do it now. My region represents a region in Cartesian space, and that'll be an issue that'll come up by the time we're done with this application. Every region has a min point, which I'm going to refer to as x min, y min, and a max point, x max, y max. And you really want to make sure you get those parameters in the right order. They're all going to be integers, for example, and it's easy to switch them by mistake and do it x min, x max, y min, y max. So you have to be careful, and for this reason we always include documentation that states what to do. This creates region from x min, y min to x max, y max. And it does what you would expect. I'm going to keep track of the x min values and the y min values. And the y max values. This now clarifies what a region is. It's worthwhile to consider the largest region that you would ever have. And that's the one that would be associated with the first node in a KD tree. It has to cover an infinite space, but we clearly can't use infinity as a number. So we'll have to come up with an arbitrary value that we consider to be the infinite on the positive side as well as infinite on the negative side. In many programming languages, there are constants that are max int and min int that you can use. Python has this ability to use big nums to store values, so there really is no concept of a minimum int or a maximum int. So we have to sort of arbitrarily choose one, which we'll do. We'll choose a min and max value that would be more or less what you would have for 32-bit integers. And I'll do that here. My max value is, this number should be somewhat familiar to people working with 32-bit numbers. That's the largest number you can get with 32-bit. But we also have negatives. It doesn't really matter what these values are. You just want to have some values that are reasonably outside the space of your application. Once I have that in place, I'm going to define that concept called the max region, because it's going to be handy to have that around. This is a default region that has the x and the y mins set to the minimum value, the x and the y max set to the maximum value. Almost done with the region, that is. When it comes time to take a partition, which is associated with a node, and insert a child, we have to take that partition and break it up into two parts. And so we need to find an easy way to be able to copy these regions. And I will put in a copy function that lets me do just that. And so this will just return a new region, which is whatever my minimum value is on the x and the y side, and then whatever my maximum value is on my x and my y side. It's worth stopping once in a while just to make sure that we're actually on the right page. Let's make one more little change, which is the KD node. We know when you create a binary node in this KD node tree, we know we want to have a point and the orientation. But what should I use for the region? Well, I need to pass that in. And until I know anything else, I'll have a default value which says just use the maximum region as your default. This would be a very convenient way to just always know that you will have a region associated with every KD node. Let's run this and see what we have been able to create. If I want to create a new KD node, I need to have a point, an orientation, and a region. How am I going to represent a point? Once again, you could use the available points if your programming language has a class or a data type for this purpose. Here in Python, we're just going to use a tuple or a list which contains two elements. And those two elements are going to be the x and the y coordinates. Now, I've done enough programming to know that I don't want to make assumptions and just remember, oh, 0th coordinate is x and the first coordinate is y. Much better to introduce constants that we can use to index into these points as needed. And so I'm going to create these two values. We'll call them x and y. And x is going to refer to the coordinate of the tuple, which is the x value, and then the y will be referring to the coordinate of the second one, which is the y coordinate of that tuple. Because x and y are so commonly used in programs, to avoid any conception, I'm just going to give it a name that will remind myself that it's actually not a value, it's an index into a value. So if I have a tuple, a point, which has two values, I want to get the x1, and that's the 0th coordinate, and the y1, which is the first coordinate. This small little syntax, again, is another way that programmers remind themselves when they're dealing with actual values or dealing with constants or other indirect references. So let's see what this looks like in my system. If I want to just create a region, I have to give it a min max on both the x and the y side. So if I just did the simple one, this is my region. I can copy it if I wanted to, or I can look at individual values. It has x min is 0, for example. And if I want to copy it, I'll get back another instance, which is a different region object. It has the exact same coordinates, but I can then take those and change them as I need to, which is something I'll be doing when I do the partitioning scheme in the KD tree. If I look back over here to my KD node, I have the constructor init ready, but I haven't yet implemented add. And so now it's finally time to complete that implementation. Once we do, we'll be able to make some good progress towards explaining how the KD tree actually works. To add a point to a KD node, we need to take special care. Once again, with the binary search tree, we were trying to require this global property that would tell you that all the nodes to the left had smaller values and all the nodes to the right had greater values. In the KD node, slightly different. Every node has an above and a below. It also has an orientation. And so when you're about to insert a point into a tree that's rooted at a specific KD node, you first have to ask yourself, well, what's the partitioning used by that node? Is it vertical, in which case above and below are dealing with the x coordinate? Or is it horizontal, in which case above and below are dealing with the y coordinate? So to make that work, we need to come up with some helpful utility functions. And what we'll do is deal with it in a very special way. First, we're going to reflect on what the KD tree is actually doing. It's storing a collection of points. Does it really matter if a particular point appears multiple times in the tree? And I'm going to argue here that the KD tree is actually set up to be not just a collection of points, but a true set of points, where any point, if it exists, only exists once in the tree. And the reason is kind of straightforward. If I'm using these nodes to partition a space, and the same node value appears multiple times, then there is no partition. It doesn't appear. It already has been partitioned up by a parent node or something. So a KD tree is different from a binary tree in the sense that you really want every value to be unique in the tree. So when I think about the add, I'm going to make a small check first and just make sure, is the point that's being added actually equal to my current point? Because if it is, I don't want to add it. I'll just return. And this is a way to protect against inserting duplicate points into a recursive structure. Now, if it's not equal, the point that I'm adding, that is, if the point that I'm adding is not equal to myself, then I have two choices to make. And it just says, well, is it above or is it below? And so you would write something that looked like this. If the point that I'm adding is below myself, then I want to insert it to the tree that's rooted at the below child. Now, it could be that there is no below child. But if there is a below child, then I say, self below, you add the point. If, however, there is no below child, then it's about time that I created it right now. However, when you're creating a KD node, I need to know the point, the orientation, and the region. So how do I make that work? We're going to introduce a helper function that does all this together. It will keep the add function simple, and it will put all the convoluted logic with regard to region manipulation and orientation flipping into a specific helper function. So I'm not just going to create a new KD node like this. I'm going to use my function, which creates a child with this point. And now I'm going to look at the opposite point of view. What if it's the case that the point that's being added is not below? That means it must be above. So I'll add the same check here. If I actually have a tree rooted at self above, then he's the one responsible for adding that point. Otherwise, I have to add the child there. Now, when I consider how to implement this create child method, it has to do a number of things. It's going to have to deal with the orientation flip. It's going to have to deal with taking a larger region and partitioning it up into smaller regions. So the function could be rather complicated. But let's take a stab at it and see how we do. If we had been doing this code in a bottom-up fashion, this would have been the first method that I would have started. But we did it in a rather top-down fashion, and so once I get this code working, the create child, then I'll be able to demonstrate the add, and then almost like magic, the whole thing will be implemented. Creating a child says I've got a point. And I need to create a child node either above or below the given node with point. So now I start with the current node that I'm in, and I need to get a copy of its region because that's the region that would be partitioned into two. This is the reason why I wrote the copy function. I now have a copy of the region. What do I do with that region? Well, if my orientation is vertical, that means that that region is going to be broken up into a left side and a right side. But I have to figure out which side. Is it the left or the right side? Or to be more precise, using the terms in this lecture, is it above and below? And so I realize I'm missing a piece of information. I need to know whether this is being added above or below. And so I go back to my add, and I say, well, look here. If you're adding the point, this child here is being created because it's below. So I will pass in true. Over here, this create child is being created because he's above. So I will pass in false. So now I know in the create child function whether the node is above or below. And that's necessary so I can take the region and break it up accordingly. So if I have a vertical partition region, then I'm going to have a left side and a right side, and that means only the x coordinate will change. Let's show you how that works. If it turns out that I'm dealing with a point that's below the vertical partition, these are the ones whose x coordinate are smaller than the vertical partition. Then I take the region that I've just made a copy of, and I say, you know what? Your maximum point, your maximum x coordinate is whatever my node has as an x coordinate. So I take that larger region with a vertical node that goes right through it, and I pull it from the right-hand side down, and I say the x minimum is the same. I'm pulling the x max down to be right where that partition is. This is the exact same analog that we do when we did the binary array search, and you wanted to search for a particular value in a binary array. You move the low or the high to be at the midpoint. Once I know that I'm looking for the below, that handles that. Otherwise, it must be above. And so I need to move my min value up, like that. But it could also be the case that the point for which I'm creating a child is in fact a horizontal node, which means that I'm partitioning above and below based on the y coordinate. The same logic will hold. If you're above, the y minimum has to change, and if you're below, the y maximum has to change. So if my code looks as follows, if below, I'm going to take this and now reference the y index value. Otherwise, I'm above, so my y min moves up to be this value. I hope you can see why I created those special constants x and y, because when you're just casually looking over code, the last thing you want to see is a bunch of zeros and ones and then trying to figure out what they really mean. It's the exact same thing that does the orientation. I set them up to be 0 and 1 because I wanted them to alternate easily from one level to the next. So the last thing I need to do here is, now that I have a region, this is the point that I want to create a child node for. I can now return that KD node. What does that KD node have? Well, it has that point. After all, that's why the KD node was created. What's the orientation of the point? It's the opposite orientation of myself. So if I'm a vertical node, it's going to switch to be horizontal. If I'm a horizontal node, it will switch to be vertical. And I associate the region with that. At this point, we now have a fully functioning KD tree with regard to inserting a node at the tree, which gets propagated down into the KD node itself. Let's run it. Let's see how well we did. As you know, there may yet be defects lurking in the code, but we'll take a chance. We start with the topmost concept. I want to create a KD tree. And initially, the root is empty. Once I have a KD tree, I want to insert a point into that KD tree. I'm just going to create a point here, and he's going to be the point 10, 10. I'm going to add that point to the KD tree. And to remind ourselves of what's going to happen, that is going to be the new root of the KD tree. So I have a root node now. Well, what is that root node? What's associated with it? Well, I can look at it and I can see that it has a point, 10, 10. I can look at its orientation. It's 1, which, as you remember, is my default that I use for vertical partitioning. What's the region that's associated with that? I have to look at the KD root, and it's called, I'm missing it out, as you can see. You never know when a defect is going to lurk here. I created my KD node class, and I had everything set in place except I forgot to store the region. Let's put that in. Let's try it again. If I take that point that I'm trying to add, I have my root. I now have a region, which is grateful for me. What's the x minimum value of the region? It's a very large negative number. What's the max value of that region? It'll be a very large positive number. So I've been able to demonstrate the insertion of a point. Naturally, you want to validate this works for any points that you keep adding. So let's just refresh ourselves on exactly what the add method is going to do. It's going to try to add a point to the tree. As long as the point is not already there, it will attempt to do so. First checking, is that point below the partitioning for that node, which could either be horizontal or vertical. If it is below, it's going to add it to the existing tree that's rooted at the current below node, or in fact create that below node for the first time. Otherwise, if the point is above, it will add it to the tree that's rooted at that node, or it will create that node. And the create child function that I spent all that time on is really responsible for doing quite a lot. It's responsible for splitting off from a particular node a new child node which has the original region cut in half, whether by the x or the y coordinate is determined by the orientation of the node. And once I've created a new region, I return a KD node which is properly set up, whose orientation is flipped and is now properly constructed. When I show you this in the code, it really won't be that impressive, because after all, we won't be able to look at it. But be patient, I'll show you a nice way of getting around that problem in a second. So here's my first defect, which, as I mentioned, I will always expect there will be a defect. Remember how I wrote this add method, and I said I know if I need it from below? Well, I never got around to writing that particular function. The good news is it's easy to write that function. If I want to know whether a particular point below current node, I now have to look at the orientation. And I put this in a helper function because it's quite useful naturally, and I don't want to confuse the logic of my add any further. If it turns out that my orientation is vertical, then I'm dealing with a horizontal partitioning, which means that this point is below if its x-coordinate is less than my x-coordinate. And otherwise, I would just return that it must be horizontal, in which case my y-coordinate must be less than the y-coordinate of the point. This small helper function handles all the orientation issues that I need as I'm traversing through the tree. You might say, well, what if the x values happen to be the same? Well, the way I treat this is that you're below if you're less than, you're above if you're equal to or greater. So at least I've covered all my bases. And now when I run this, I will once again create a KD tree. I'll add my point 10. I'll add a point 20. And you can't really see much change, right? The point that's associated with the root is still 10. Now you'd say, well, where is this point? Where did it get placed? Well, if it's a vertical partitioning, and I'm looking to see where the point 20, 20 is, it has to be to the right, which means it has to be above. So the root has an above tree as a subchild. The root does not have a below tree, because I only added a point to the above. I could do this for a number of times and show you all this structure, but I think it's a lot better to show you an actual application demonstrating this in graphical form. So this segment completes the implementation of the KD tree. It has a node, which has all the structure that I want. I've defined a region, which is necessary to capture the information associated with the partitioning. I have some very useful constants that will come in handy. And I have a tree that for now allows me to add points to it. With this in hand, we're ready to do a graphical user interface to show you how this works.